So Lagrange, I just grabbed some problems from another textbook here. Let's see. Let's try this one. Let's try using a better pen. I can't remember if today is my nephew's birthday or if it's tomorrow. He's turning 10. I'm gonna take him to see Green Day. Yeah. In San Francisco. In September. Yeah, that's when they're gonna be in San Francisco. My nephew, he really likes Green Day. They were not cheap. For the three of us, I think it was like $600.
Oh my gosh.
Yeah, I know. And those were like the cheap seats.
It's like we're way up.
Yeah, no, we're way up there. But it should be fun. All right. No, I think we're gonna tell him today or tomorrow. Like we send him a card and he's gonna like call us and we're gonna be like, for your birthday, we're giving you. Yeah. But it's funny, the other day he was saying like he was watching the Grammys with his parents, and he's like, I really want to go to a concert. His mom was like, who would you want to see? He's like, Green Day, obviously. And so I think it'll be a good birthday present. I know, right? Okay, let's try this. So let's find the maximum and minimum value of 3x. So if I was writing this, I would write it as f of x comma y equal to 3x minus y plus 6. Subject to or on the circle, but let's say subject to the constraint. X squared plus y squared equal to 4. And if I were doing this problem on a test, the very first thing I would do is I would take that constraint and I would rewrite it as g of x comma y equal to x squared plus y squared minus 4 equal to 0. Take your constraint equation, bring everything to the left or whichever side you like, and then call that g, and then set it equal to 0. Okay. Always the same first step, or I should say, for one constraint, always the same first step. We're going to set the gradient of f equal to lambda times the gradient of g. If it's a 2 constraint, it's the lambda times the gradient of g plus mu times the gradient of your other constraint. Which we can do a 2 constraint one if you want. All right. So let's see. So gradient of f, just do each part individually. So first set the partials, each of the x partials equal to each other. So that's going to be fx equal to lambda times gx, which I suppose you could skip writing and just write that fx is 3 and lambda times gx is 2x. Similarly, fy is going to equal lambda times gy is going to become -1 equal to lambda times 2y. All right, I'm going to solve this the way that he seems to prefer doing it. Either way is fine, but figuring out what lambda and mu are, if there's a mu, is probably more complete. So here's what you should do if you want to do it the way he's doing it. Take these equations, if you can, and isolate x and y in terms of lambda or mu or whatever your Lagrange multiplier is. So we're going to solve for x here and get x equal to 3 over 2 lambda. We're going to solve for y here and get y equal to -1 over 2 lambda. And then we're going to take those and plug them into the constraint equation. So then our constraint, which I would probably still actually write as x squared plus y squared equal to 4, x squared plus y squared equal to 4 becomes 3 over 2 lambda squared plus -1 over 2 lambda squared equal to 4. Which is going to allow us to solve for lambda. Have questions, don't hesitate to ask them. Mm-hmm. So this equation here, how did I get from here to there? What did I do?
Where it's like 3 equals lambda times.
Oh, how did I get the 3? Good question. Well, so I'm taking this equation, so my 3 should be what? It's the partial of f with respect to x. There's my function f. What's the derivative of that with respect to x? Right, how about with respect to y?
Oh, for the next one?
Yeah, right. That's what those are coming from. So then simplifying this, 3 squared is 9, 2 lambda squared is 4 lambda squared, and then negative 1 squared is 1, and then 4 lambda equals 4. You could put these together. Yeah, we should put these together. I might, in a different sense, if like my numerators were more complicated than just constants, I might just make the next step be multiplying both sides by 4 lambda squared. Like if it was like 9x plus 3y or something equal over this, then I would just multiply by common denominator. Here, it's easy enough to add this together and say 10 over 4 lambda squared equals 4. So then 10 equals 4 times 4 lambda squared. And then 10 divided by 16 is equal to lambda squared. So then lambda is equal to plus or minus the square root of 10 over the square root of 16. And then we can go back and find x and y. It'd be kind of gross. All right. So lambda equal to positive root 10 over 4 is going to give me x equal to 3 over 2 times lambda, and y equal to 3, sorry, not 3, negative 1 over 2 times lambda. Technically, I don't have to find x or y. I mean, I kind of do, but like you get away with that doing. Because so I should be more specific here. What's the question asking me to find? It's asking me to find the maximum value of the function and the minimum value of the function. I do kind of define x and y to be able to find those things, but I actually need to plug those points into the function and figure out what the value actually is there. So if I plug those in, that's kind of gross. I'm going to try and simplify this a little bit. Ew, I do not love this. This is equal to 3 over root 10 over 2, which is equal to 6 over root 10. And the y value is negative 1 over root 10 over 2, which becomes negative 2 over root 10. Yeah, we could rationalize those. I really don't want to. So if we plug those into the original function, f of 6 over root 10, comma, negative 2 over root 10. And again, reminding you all that the original function is 3x minus y plus 6. That's going to be 3 times 6 over root 10 minus 1 times negative 2 over root 10 plus 6. And that's going to be what, 18 plus 2 is 20. 20 over root 10 plus 6. Which, yeah, not my favorite thing ever. If you really, really wanted to rationalize it, it would be 20 root 10 over 10 plus 6, which then becomes 2 root 10 plus 6. I don't know if that's the max or the min yet because I haven't checked the other critical point. Now, here's where you should try to save yourself some work. The other value of lambda is negative root 10 over 4. It's not going to change a whole lot except for the signs. So if lambda is equal to negative root 10 over 4, then I can see that x is going to be the same as it was except the opposite sign. So I shouldn't write all this again. I should just say x is going to equal negative 6 over root 10, and y is going to equal positive 2 over root 10. And that would be a totally fine thing to do on an exam. If you can see that plugging in this gets you something and plugging in this will get you the opposite value, you don't have to go through all this work again. And then finally, if I plug those in, f of negative 6 over root 10, comma, positive 2 over root 10, should end up getting me a negative 18 minus 2, so that's going to be a negative 20 over root 10 plus 6, or if you prefer, a negative 2 times root 10 plus 6. That's the maximum value because it's bigger. That's the minimum value because it's smaller. Excuse me. Kind of gross numbers. I just pulled this one from a textbook though, so I didn't have any expectation the numbers wouldn't be gross. But I wouldn't expect super nice numbers on the test unless the functions were really simple. What else to say about this one? You could have gotten through this without solving for lambda if you wanted to. Let me point. I think it's worth pointing out. So let me just show you what I mean. I'll try and spend too much time talking about this. So I could have from here said, instead of solving for x and y, I could have solved both of these for lambda. Meaning I could have said 3 equal to lambda times 2x gives me 3 divided by 2x equal to lambda. And similarly, negative 1 equal to lambda times 2y gives me negative 1 divided by 2y equal to lambda. And then set those equal to each other, which gives me 3 over 2x equals negative 1 over 2y. Cross multiply, you get 6y equal to negative 2x, or 6 divided by 2 is negative 3y equal to x. And then you can plug that into your constraint and kind of bypass using lambda completely. If you plug that back into your constraint, then I can say that x, instead of x squared plus y squared equal to 4, now I'm going to get negative 3y squared plus y squared equal to 4, which gives me 9y squared plus y squared equal to 4. So 10y squared equals 4. Y squared equals 4 over 10. Y equals plus or minus the square root of 4, which is 2, over the square root of 10. Which are the values we got for y, I hope. Let me go back and look. Let's see, y. Yeah, those are the values we got for y. We got y equal to negative 2 over root 10 and positive root 2. So it's this, it'll get you to the same place typically. Sometimes things are a little weird though. So either way should be fine. You kind of have to pick what you think is better for you. I didn't like, so that I should say, I wouldn't stop here. Then I go back and I say, oh, well then x is 3 times that. So if y is equal to plus or minus 2 over root 10, then x is equal to negative 3 times plus or minus 2 over root 10, which I will point out we often write as minus plus 6 over root 10 to indicate that these have opposite signs. That one's positive, that one's negative, that one's negative, that one's positive. And then you plug those into the original function to see that it was a max, or to see what the values were, like we already did. So I think this is less work personally. Sometimes, depending on the complexity of your functions or your constraints, it can be better or necessary to solve for lambda and or mu. Questions about that? You know, that's a better question for.
But I was thinking, like, if we did that.
I mean, I don't think he should care, but that doesn't mean he doesn't. I honestly don't know. I couldn't say one way or the other. Would he care or not if he didn't solve for? I could imagine him writing problems where it was more necessary to solve for lambda or mu. So let's look at another one. Sorry, just so we can see something maybe a little more complicated. Yeah, sure. All these other ones are 2 constraints though. Sure, we can do a 2 constraint one. Just to kind of talk about how you might have to do it. Let's do a 2 constraint one, and then we will talk about some limits. So let's say we want to max. I feel like I had some, oh, there's some, yeah, sure. Let's say we want to maximize f of x, y, z equal to x squared plus 2y minus z squared, subject to the constraints 2x minus y equals 0, and y plus z equals 0. So again, you should immediately view this as g of x comma y comma z, really. Like, I think you should write all the variables that are in play, even though it's not a function of z, equal to 2x minus y equal to 0. And here you have h of x comma y comma z equal to y plus z equal to 0. And I do think it's worth just writing the general kind of setup, which is that we're going to set the gradient of f equal to lambda times the gradient of g plus mu times the gradient of h. I like writing little arrows because gradients are vectors, but you don't need the little arrows. I also think I really do like writing out the formula. So fx equals lambda times gx plus mu times hx, and fy is going to equal lambda times gy plus mu times hy, and fz is going to equal lambda times gz plus mu times hz. I know I've got all that written right here technically, but I find it helpful to write it all out still anyway. You don't have to. You can totally skip writing this and just say, oh yeah, I know what fx is, it's 2x. I know what lambda times gx is 2. I know what mu times hx is 0. And I would do whatever minimal simplification you can right after that. Like here, it's really easy to divide both sides by 2 and just say, oh great, x equals lambda. Nice. Why don't you all find the next two equations? Find this equation and this equation. Don't simplify them at all. Just find the first step of each equation. That's what your equation should look like. Fy, the partial of this with respect to y should be 2 equals lambda times the partial of this with respect to y is -1 plus mu times the partial of this with respect to y is +1. Similarly for the third coordinate, whatever, fz is -2z equal to lambda times gz is 0 plus mu times hz is 1. So those are our equations. And similarly, just like in the first equation, I would definitely rewrite this one. I probably wouldn't even actually write the lambda times 0 here if I was actually doing an exam, but it's nice to see here. I would just say, oh yeah, great. -2z is equal to lambda. Is the what? What should -2z actually be equal to? Did I miswrote? Mu. And then up here we have 2 equal to negative lambda plus mu. I would probably rewrite that as mu minus lambda just to, because I like positive things first. Okay. Now what? Now what is the big question, right? Like once you've gotten to this place where you've gotten your equations with all these things, then you have to kind of decide what to do. And the hard part here is that none of these equations have a y in them. Right? I don't see right, there's no y here, there's no y here, there's no y here. So I might have to instead, yeah, what am I gonna do? Oh, I see what I could do. So I could plug either one of these into the constraint to get y in terms of lambda or mu. Here's what I mean. Is that what I mean? To be perfectly frank here, I don't actually know what I'm supposed to do next. Like I'm gonna try stuff. It might not work out that well. So here's what I'm seeing. I've got the following equation. I've got 2x minus y equals 0. And I've got y plus z equals 0. I also have the stuff I just came up with. X equals lambda, 2 equals mu minus lambda, and negative 2z equals mu. I think I see the way. But again, it's really kind of just like, it's dicey. There's a lot of things you could do. I can see here that if I plugged in negative, I'm trying to do it the way I want to do it. I'm gonna do it my way, and then we can go back and see if we can do it the other way. So here's what I'm seeing first. If I plug, let me be more general. I would love to get to a place where I had as many equations as variables. Technically, that's true, but I'd really like that to be true with just x, y, and z, because that's what I actually care about. I don't give a shit about mu and lambda, right? They don't matter. They're just helping us find the answers. We don't actually have to find them, although we might have to if he wants us to. So what I would really love to have is 3 equations with x, y, and z. So great. Throw negative 2z in for mu and x in for lambda to get a third equation that just has no mu's and lambdas. So I see that 2 equals negative 2z minus x. So now I have 3 equations and 3 unknowns. And I can probably figure out what to do with them. Like, for example, if I took here and said z equals negative y, and here I said x equals y divided by 2, right? 2x equals y divided by 2. I can then plug both of those in over here to get 2 equals negative 2 times z, which is negative y, minus x, which is y over 2. And then I can solve for y. This is not the only way to do this. So here I'm going to get 2 equals 2y minus y over 2. That's going to give me 2 equal to, I'm just going to factor out a y. Say it's y times 2 minus a half. So 2 equals y times 3 halves. So 2 times 2/3 equals y. So y is 4/3. And then I can plug that in here and get z equal to negative 4/3. And then I can plug that in here and get x equal to 1/2 times 4/3, which is 2/3. Not done, because we haven't plugged it back into the original function to see what the maximum value actually is. So plugging it back into the original function, we're going to say the maximum value. How do I know it's the maximum? Because they told me to maximize. Honestly, that's how I know. Because they told me that's what I was doing. If they said find the maximum and the minimum, I would have to have gotten at least 2 critical points and plugged them in. And then the bigger one would be the maximum and the smaller one would be the minimum. So maximum value is going to be f of 2/3, 4/3, negative 4/3, which is going to be 2/3 squared plus 2 times 4/3 minus negative 4/3 squared, which is 4/9 plus 8/3 minus 16/9. 4 minus 16 is negative 12, so negative 12/9 plus 8/3 is negative 4/3 plus 8/3, which is 4/3. Gross. I don't know if I can solve for lambda. I mean, I guess I should be able to, but I don't know, it just doesn't seem good to me.
So if it asks
asks for a maximum and minimum, you would end up getting 2.5.
I would say we ended up getting at least 2 critical points. But sometimes you get more, like one of those homework problems, there was like 4 critical points, and 2 of them gave the maximum value, and 2 of them gave the minimum value. But you could have 4 critical points, and 1 could give you a max, and 1 could give you a min, and the other 2 could give you something in between. I'm looking at this trying to think about how I would solve for. Yeah, I don't see it. Yeah.
Get the first and the second equation again.
Which when you say the first thing, which equations do you mean? Like here, so those are my constraints. So those are given to us from the get-go, right? We were told to math. So normally, like if you looked at his homework solutions, you'll see that he writes down like the first 3 equations, like I have here. Like he would have written down these 3 equations here, and then below that, he also would have written that 2x minus y equals 0 because we were told that that's a constraint, and x plus z equals 0. I just don't feel a need to write, y plus z, y plus z. I just don't feel a need to write that equation again because we already have it on the page. But that's where those are coming from.
So you're solving for third one using those?
Well, so usually here's the deal. Right here, if I just look at my constraints, I have 2 equations and 3 unknowns. I don't have enough equations. I'm going to use these other 2 garbage variables to help me find a third equation relating my 3 nice variables. That's what I've done on the second page here. I've said, oh, well, if x equals lambda and negative 2z equals mu, I can then get an equation relating x and negative and z, because I happen to have this equation in the middle here.
Okay.
But really, I mean, it could have gone a very different direction, right? There are lots of other ways we could have solved this. It's just I was looking and that seemed to pop out to me. That, oh, I've got mu equals something with z, x equals something with lambda, an equation with just mu and lambda. So if I plug those in there, I'll have an equation with just x and z.
So.
Right,
Okay.
exactly. There are variables that are made up. And do we need to find them? As far as I'm concerned, no. But that might not be actually true. He might ask that. Now, I will point out here that we could go back and say what they were. Because if you know that x is 2/3, then you know that lambda is equal to 2/3. And if you know that z is equal to negative 4/3, the mu is going to be positive 8/3. There's no value there, in my opinion, but that doesn't mean we couldn't be asked to do it.
Where did you get 2/3 from? The x equals 2/3?
So when I was solving this, so I plugged this in here, I plugged that in there, right? So I took this equation, x equals lambda, mu equals negative 2z. I plugged this into this middle equation here. And then I solved it. So I had 2 equal to negative 2z minus x. And then I said, oh, but I can use this equation here to say that x equals y over 2 and plug that in over here to get y over 2 for the x value. Similarly, z equals negative y I plugged in here to get negative y for z. And then I have one equation with just y's in it. I can solve for y. So I simplified this. I had negative times negative y is 2y minus y over 2. I factored out a y just to make it easier to see. That you have 2 on the left equal to y times 2 minus 1/2, which is 3/2. So 2 equals y times 3/2, and then multiply both sides by 2/3 to get 4/3 equal to y. And then, since x is half of y, half of 4/3 is 1/2 times 4/3, which is 2/3. That's coming from right here. And then similarly for z, since y is 4/3 and z equals negative y, z is going to equal negative 4/3. So basically, once you have one of the variables and you have the other variables written in terms of the other variable, you can go back and backfill them essentially. Okay. Again, try not to worry too much about the Lagrange, right? There'll probably be a Lagrange problem on there. It probably won't be too terrible, but it's not the entirety of your exam. So it shouldn't be the only thing you think about. Let's look at a few limits though. Because I know it's been a minute since you talked about a limit. So let's say we got the limit as x comma y approaches 2 comma 1 of 4 minus xy over x squared plus 3y squared. I don't see any factoring. What should I start doing? I should always try to plug in the point before I do anything else. So if I plug it in, I get 4 minus 2 times 1 over 2 squared plus 3 times 1 squared. And that's going to be just a real number. So I'm done. 4 minus 2 is 2. 4 plus 3 is 7. That's my answer. I don't imagine that you would have one that easy on your test, but it's always good to be at least thinking about before I do anything else, I should try to plug it in. Okay, let's look at a different example. Let's say I have, again, the limit as x, y approaches 2 comma 1. And now it's going to be, sure, x squared minus 4y squared over, sorry, I'm trying to think of something clever here. Snap, sorry, 1 sec. I have to take a minute to be clever. Sure, that's clever. Yeah. XY, yeah, minus 2y minus x plus 2. Ooh, that's I might have been too clever for my own good here. Yeah, I feel real dicey about this. Sorry, I was trying to come up with something smart, and that let's skip this. So here's the problem. This factor is kind of like the way I was trying to be super smart, and it was not super smart. If you plug in 2, 1, you obviously get 0 over 0. And then if you factor this, it does factor, but I think not very helpfully. The top factors as x minus 2y times x plus 2y. That's great, I guess. The bottom factors as x minus 2 times y minus 1. And doesn't really help us very much here. So I made the bad problem. We should skip it. Here's what I kind of meant to do. Let's try that. Let's try this again. Instead, what I was going for was something more like the limit as x, y approaches 2 comma 1. I wanted the numerator as is. And I wanted the denominator to be, fine, I'll just make it how I want it to be. X minus 2y times x plus 3x plus y. There. That's what I was going for, really. Which I suppose I could have started out writing if I could have done the math fast enough in my head as x squared minus 4y squared on top, and 3x squared minus plus minus 5xy minus 2y squared. So let's say we started with this. And if we plug it in, we're going to get 4 minus 4 over 3 times 4 is 12, minus 5 times 2 times 1 is 10, minus 2 times 1 is minus 2. We get, not surprisingly, 0 over 0. Okay, so if I was going to try and do this problem, here's the thought process I would want you to see, because it might be hard to see that this bottom part factors like this. But here's how you can kind of sneakily get there. This is going to be the limit as x, y approaches 2 comma 1. We can factor the top. X squared minus 4y squared is the difference of squares. We've already factored it up here once. x minus 2y over x plus 2y. So now let me ask you all, of these two factors, which is the quote unquote problem factor? The x minus 2y or the x plus 2y? Right, that's the part that's giving us a 0 on the top. It's also, so if we're getting 0 over 0 and you can identify the factor that's giving you 0 on the top, that's also the factor we need to look for in the bottom so that they can cancel out and not have those 0 over 0s. So I would love it if I had an x minus 2y in the bottom. So then I'm just going to make up what the other part should be. So I know that x times something has to give me 3x squared, so that better be a 3x. I know that negative 2y times something has to give me negative 2y squared, so that better be a plus y. And then we check the middle terms to see if they work. It is, but I was pretending like that wasn't there.
Okay.
Yeah, I was saying like, if you were not given that, and you just started with this, and you started, you had 0 over 0, then we can see the one part's relatively easy to factor, the other part's not, but we know that we want x minus 2y to be one of the factors. And then we're like, oh, well, that has to be a 3x so that that multiplies right. That has to be a y so that that multiplies right. And then the middle terms work because you get a minus 6x, sorry, minus 6xy and a plus xy. And let's add up to minus 5xy. And then you can go along and cancel the problem factors and then plug in for the rest and get 2 plus 2 on top over 6 plus 1 on the bottom, which is 4 over 7. But honestly, if you're faced with a limit problem on your exam, it'll probably be one where you're approaching 0 over 0. So for example, you might have something like, sure, the limit as x, y approaches 0, 0 of, yeah, like that, 6x cubed y over 2x to the fourth plus y to the fourth. And when you're going through 0, 0, we're always going to approach these, especially going through 0 over 0 ones, with the attitude that the limit probably doesn't exist. So we're going to try some paths. And I really would imagine if you had one that existed, they'd probably tell you it existed and ask you to show it, because it's hard to know it's going to exist unless you have a lot of experience. So I would first try what path? X equals 0 or y equals 0 definitely should be on your playlist. So x equals 0, we're going to get the limit as x, y, really just x, or sorry, really just y approaches 0 of 6 times 0 cubed times y over 2 times 0 to the fourth plus y to the fourth, which is just the limit as y approaches 0 of 0 over y to the fourth. 0 over y to the fourth is 0, and the limit of 0 is 0. Sometimes plugging in x equals 0, y equals 0 won't help you because the top and the bottom will both 0 out before you get to take the limit. Like if this had been 2x to the fourth times y to the fourth in the bottom, then plugging in 0 for x would not have been great because we would have 0, 0. But most of the time, that's not going to happen. So now we try another path. And I'll point out that usually, if you tried x equals 0 and you got 0, trying y equal to 0 will probably also get a 0, and it will here. So let's try a different path. X equals y seems like a great choice. And I think that's a great choice because we can see that if we do that, the degree on top and the degree on the bottom are going to end up being the same. So you can either replace the x's with y's or the y's with x's. It doesn't matter which you choose. Let's replace the x's with y's and say we have limit as y goes to 0 of 6 times y cubed times y over 2 times y to the fourth plus y, which is going to be 6. Oh, sorry, the limit as y approaches 0 of 6y to the fourth over 2y to the fourth plus 1y to the fourth is 3y to the fourth. The y to the fourths cancel, and 6 divided by 3 is 2. So the limit as y goes to 0 of 2 is 2. And that's enough to say that the limit does not exist. So the limit is x, y approaches 0, 0 of 6x cubed y over 2x to the fourth plus y to the fourth does not exist. If you want to write more words, the more words would be because different paths have different values. Or have different limits. And that's enough. What else is on your mind? Oh, chain rule. Chain rule. Let's do a chain rule problem. I should just look in the book. Instead of trying to make something crazy up, I'm just looking in the book. Sure. Yeah, let's do some trig. Let's say we have f of x comma y equal to x cubed times tangent of, how the rest do we want this to be, James? Not by Chris. Y squared. And then x of t comma s is equal to t squared natural log of s. Y of t comma s is equal to, sure, sine of t plus 5. 5 is a terrible choice. 6s. It's only terrible because my 5s and my s's look similar. That's why it's a terrible choice. Okay. Find del f del s and del f del t. Yes, they are dels because at the very base level, f is a function of t and s. So del f del t and del f del s are both partial derivatives. Okay, I always recommend drawing the little map. So at the top level, you got f. F depends on the variables x and y. And then at the next level, x depends on the variables t and s, so does y. So I would draw it like this. And then like that. You don't need this map if you know how things work, but I have always found it helpful, and I've been doing this for 25-ish years. So I would draw the map personally. So now if I want to find del f del s, I would write it out, meaning write out the whole thing just in terms of your derivatives. So it's going to be the path that gets you to s. So either through x and then to s, that's going to be del f del x times del x del s, or the path that goes through y, del f del y times del y del s. If you look at each of these paths and you think about canceling the things that would cancel if it was fractions being multiplied, you'd be left with del f del s and del f del s, which is what you should be left with. Every path should kind of reduce down to the thing you're trying to find. You shouldn't think about the fact that you're like, or the, not the fact, you shouldn't think about it as like you're adding del f del s plus del f del s. Don't worry about that. That is not something you should be thinking about. They're both paths are working great. So now we're going to find the things. So del f del x is going to be 3x squared times tangent of y squared. Del x del s is going to be t squared times 1 over s. And we're going to leave our answer in terms of x, y, and t and s instead of plugging everything in for t and s, probably. Del f del y is a little bit worse. It's going to be x cubed times what's the derivative of tangent of some stuff? Secant squared of the stuff times derivative of the stuff. And del y del s is going to be 6. And then if you really, really wanted to, but I don't really want to, you could plug in x equal to t squared natural log of s and y equal to sine of t plus 6s for each instance of x and y. But you'd have to plug it in here and here and here and here and here, which seems kind of terrible to write out. But if they said to write del F del S only using S and T, that's what you would need to do. Let's find the other derivative we've been asked for. Here's the good news. We've already done half the work we need to do to find del F del T. Here's what I mean. Del F del T, if we find all the paths, del F del T is del F del X. Again, it hasn't changed. It's going to be the same thing we already found. We don't have to think about doing that derivative again. Times, now it's going to be del X del T plus del F del Y times del Y del T. But look, here is my del F del X. There is my del F del Y. I don't need to think about taking that derivative again. So del F del X is going to be 3x squared times tangent of y squared. Del X del T, I do have to think about taking again. So, or taking newly, I should say. So the partial derivative of x with respect to t is going to be 2t to the first times natural log of s. Plus del F del Y is all this again. X cubed times secant squared of y squared times 2y times the derivative of y with respect to t is going to be cosine of t. And then again, if we wanted to or were required to, we could plug in t squared natural log of s for every x and sine t plus 6s for every y.